Hey everyone, I'm Alex, and I'll be giving the 11th lecture for the ZK Learning online course. In this lecture, we're going to hear about some theoretical aspects of the proof systems that you've been learning about throughout this course. This includes both some very important ideas dating back to the foundations of the field in the 80s and 90s, as well as some much more recent results just from the last few years. Let's start with a high-level overview. Cryptographic proof systems are one of the most important foundations of both theoretical and applied cryptography, and they have been for many decades. So for most of the course, you've been hearing specifically about SNARKs, which currently have a lot of practical relevance due to potential applications in the blockchain space. But long before blockchains existed, proof systems were still crucial for practical internet security. In particular, the entire notion of authentication, or digital signatures, is essentially a form of proof system, and so any kind of secure communication on the internet relied on it. So that's on the practical end. On the theoretical end, proof systems, and especially zero-knowledge proof systems, have been sort of a Swiss Army knife in cryptographic constructions. And the most prominent example of this is in secure multi-party computation. So this is a cryptographic primitive that tries to enable a bunch of mutually distrustful parties to jointly compute an arbitrary function of their private inputs. And zero-knowledge proofs enable you to compile a semi-honest protocol, a protocol which is only secure if you're promised that all of the participants follow the protocol exactly as specified, into a fully secure protocol where you don't assume that, where the adversary may deviate. And the zero-knowledge proof is used in a very direct way. You have each party prove that they are following the protocol specification as they're supposed to. So more broadly, zero-knowledge proofs are a critical tool in any sort of situation where you want to enforce a pre-specified behavior but simultaneously maintain secrets. And this comes up in all sorts of contexts in cryptography. So given this overview, let's talk a little bit about what theoretical research on cryptographic proof systems typically looks like. And there are sort of three overlapping categories of thoughts that I want to give you on this. So the first is that there is a lot of thought given to the question of feasibility. Do protocols with properties X, Y, and Z exist in principle? So the most prominent example of this is, of course, SNARKs. And we're still trying to understand today what we can say about whether or not SNARKs can mathematically exist, and I'll get into it in this lecture about what the issues are. But beyond SNARK specifically, there are tons of other kinds of protocols. For example, like non-succinct protocols satisfying zero knowledge, or weaker hiding properties like witness indistinguishability, witness hiding. List any collection of nice properties that you'd like from a protocol, and it may be inspired by some application, and then you can ask, mathematically, can such a proof system exist? And this question is often very complicated, and it can depend on the attack model that you're thinking about. So, for example, the problem becomes harder if you think about an adversary that might be able to open up a bunch of concurrent executions of a protocol and sort of use these executions jointly to try to break security. Things can also be more difficult if you have an adversary that has access to, for example, a quantum device. Then it's much less clear when protocols are zero knowledge against quantum attacks, for example. So there are lots of feasibility questions that come up. On top of that, we also want to minimize the assumptions that we're making in our constructions to whatever extent that is possible. So a couple of things, let me mention a couple of specific examples. So in non-interactive protocols, you often have some sort of trusted setup. Either you assume that they're like a really arbitrary trusted setup of some like structured reference string has been set up by some third party that the prover and verifier have access to, or you assume they have access to just a bunch of random coins, which is a weaker assumption, or you don't assume anything. This is called the plain model. So there's no setup, and feasibility of different kinds of protocols can certainly depend on what kind of setup you're assuming. And we'd like to have the weakest setup possible for any kind of protocol that we're thinking about. On top of that, we would like to have a proof of security or security reduction for our protocols, based on preferably simple, well-studied, and quote-unquote falsifiable assumptions. And I'll get into this a little bit more in the middle of the lecture. Then finally, especially once the feasibility questions have been resolved, we also think about improving the efficiency of various kinds of protocols. And there are many axes where you might want to improve efficiency. In the interactive setting, you might want to minimize the number of rounds of communication. Sometimes non-interactive is impossible, but you still want to minimize the number of rounds of communication. That's a resource. You might want to minimize the amount of communication, like the number of bits sent between the prover and the verifier. You might want to optimize the computational efficiency of the prover and the verifier. And this last thing, the prover, especially the prover computational efficiency, is a lot of what you've been hearing about in the class so far. But all of the ideas that you can see on this slide are more broadly what theorists are often thinking about. And then, of course, on top of that, we also think about how to apply various kinds of cryptographic proof systems to other applications that are not strictly in the cryptographic proof sphere. So that was a somewhat abstract discussion. So let's dive into a particular example of theoretical questions that come up when talking about interactive zero-knowledge protocols, which you heard about in the first lecture by Shafi. So when we talk about interactive zero-knowledge protocols, we're in a setting with no trusted setup. So the prover and verifier can send each other messages, but there's no trusted third party, there's no common random string that they have access to. What they send is all the information that they get to see. So in this setting, zero knowledge turns out to be much trickier to reason about than in the non-interactive setting with trusted setup. And the reason is that you want your protocol to be secure against an arbitrary polynomial time verifier, which may or may not follow the protocol specification. In the non-interactive setting, there is no protocol for the verifier to cheat. They're just sent a message. But now they might send messages that they're not supposed to, and this might violate security, so your analysis needs to rule this out. So nevertheless, we saw in lecture 1 that you could build a zero-knowledge proof system for any NP language, and the base protocol that you saw had some inverse polynomial soundness error in 3 messages. And so that's nice, but not really what we're looking for. We want a protocol where a prover can only trick the verifier with some exponentially small probability. So we need to think about how to reduce the error in this protocol. And so there are a couple of things you can do. One is that you can repeat that protocol over and over again sequentially. And you can show that this works. This will reduce the soundness error, but preserve zero knowledge. However, this would result in a protocol with, say, 30,000 rounds of communication or something like that. And this is not something anybody would ever want to run. So that's one option. Another thing you could try to do is repeat the protocol many times in parallel, and this is a very common thing to do. And you can show that this reduces the soundness error, as you would expect, at least in this particular situation. And it does for any statistically sound protocol, it turns out. But it turns out that this parallel repetition transformation does not actually preserve zero knowledge of the protocol, and so you have to be a lot more careful in the interactive setting. So let's see what the issue is. So let's recall what the protocol was from the first lecture. So one of the protocols that you saw was a protocol where the prover wants to convince the verifier that a certain publicly known graph is 3-colorable. And so the way the protocol works, if the prover knows a 3-coloring of the graph, is as follows. First, the prover takes its coloring of the graph and randomizes it. So each of the colors, it assigns a random 0, 1, or 2. Then the prover commits to these randomized colors. So for every vertex in the graph, the prover commits to a number 0, 1, or 2, and sends all of these commitments to the verifier. These commitments bind the prover to the assignments, the coloring assignments, but at this point in time, the verifier does not know what the colors are. After these messages are sent, the verifier samples a single random edge, which we call the challenge, from the graph, and sends this edge to the prover. And then the prover is required to open the two colors, the colors for the two vertices on this edge. And if the prover actually committed to a 3 coloring, then the verifier will see 2 different colors. And the verifier will accept if it indeed sees 2 different colors. This is sound because the prover was committed to the coloring before the edge was sampled, and so whatever this coloring was, if it's not a valid 3 coloring, the verifier would have at least inverse polynomial chance of sampling an edge that the prover would be unable to open an accepting response with respect to. On the other hand, it's zero knowledge intuitively because for any fixed edge that the verifier could ask, the prover is going to open up 2 random unequal colors, and it doesn't seem that the verifier really learns anything from seeing 2 random unequal colors. So to formalize this, we turn to the simulation paradigm, which you again heard about in the first lecture. So a quick recap. So here's how you would write down a zero knowledge simulator for this protocol. So we start with an arbitrary verifier v star, which may behave not as specified. So it may not sample a random edge. It may pick a particular edge carefully that it wants to learn some information about. And this edge may be a function of the prover's first message. But nevertheless, we want to show that we can simulate the verifier's view without knowing a coloring of the graph, a 3 coloring of the graph. And the way we do it is as follows. We repeatedly guess a random edge, and then we commit to a coloring that respects this particular edge. So we make sure that this edge has a random pair of unequal colors assigned to the 2 vertices. You can commit to all zeros everywhere else, for example. So you send those commitments over. Then the verifier, you run the verifier picks some edge, potentially maliciously. And then if the edge the verifier sends is equal to your guess, then you can send the opening, and it looks exactly like what the verifier would see in the real protocol. If your guess was wrong, then we rewind the verifier, we rewind the entire execution, and we start again. We come up with a new guess, new commitments, etc. Because the commitment is hiding, the verifier does not know which edge we guessed, and our guess is in fact going to be correct with inverse polynomial probability. So after a polynomial number of attempts, we're going to successfully create a transcript that looks like what the verifier would have seen in a real execution of the protocol. So that's how you show that this protocol is zero knowledge. So what happens if we repeated this protocol many times in parallel? Let's see what goes wrong. So I'm imagining that we have some t number of repetitions of this protocol, and we're thinking of t as pretty large. It needs to be pretty large, in particular at least security parameter, in order to make the soundness error small. But if there are a large number of repetitions, then the simulation strategy that we just described does not work anymore. It's not efficient. And the reason is that there are at least 2 to the t verifier messages that could be sent. If you guess one of them at random, then it's only going to match what the verifier sends with probability 2 to the minus t. And so you would need to do this 2 to the t times in order to successfully simulate. So the simulator would not run in polynomial time, and so the protocol does not satisfy the zero knowledge property. At least we have not shown that it does. So that's an explanation for why the simulation strategy we discussed does not work for the parallel repeated protocol. But it turns out that the protocol morally should not be thought of as zero knowledge. So there's this result due to Dwork, Nauer, Reingold, and Stockmeyer from '99, and they show this kind of funny lose-lose situation. There are two things that you might expect to be true for this parallel repeated protocol. One, you might expect it to be zero knowledge, and two, you might expect to be able to instantiate Fiat-Shamir for this protocol. And they show that at least one of those has to be false. So either you cannot instantiate Fiat-Shamir for this protocol, or if you can instantiate Fiat-Shamir for this protocol, then the interactive protocol is not zero knowledge against malicious verifiers. And I won't get into the details, but the point is basically that the bad verifier that you can't simulate here is a verifier who generates its challenges maliciously by hashing the prover's message. So the takeaway here is that we shouldn't expect this protocol to be zero knowledge. The correct intuition is that Fiat-Shamir should be possible, and we'll discuss it later in this class. But as a result, we don't think this protocol is zero knowledge. So that's an example of one issue that comes up when thinking about the theory of interactive zero knowledge protocols. And the fact that parallel repetition doesn't preserve zero knowledge causes a whole bunch of problems that come out of this fact. And so there are many lines of research devoted to sort of circumventing this problem. So, for example, because of this issue, it's not clear how many rounds of communication you need in order to prove something in zero knowledge. Like, what is the minimal number of rounds of communication of a zero knowledge protocol that actually achieves small soundness error? So there's a very recent work of Bitansky, Kalai, and Paneth, who give a construction that requires only 3 rounds of communication, which we know would have to be optimal. We know that you can't do less than 3, and they give a candidate construction for a 3-message protocol. So here are some other questions that you could ask. Forget about the rounds of communication. How efficient can you make the prover in a zero knowledge protocol? And so there are many lines of work devoted to writing down protocols that have much better prover efficiency than this zero knowledge protocol for 3 coloring that I just gave you. In particular, if you want to prove some other statement that does not naturally have the structure of a 3-colorable graph, then in order to use the protocol that we just talked about, you'd have to reduce the problem you care about to a 3-coloring question, and this reduction has terrible overhead, such that you would never want to actually run the 3-coloring protocol after computing this reduction. So, on the other hand, there are other constructions of zero knowledge protocols that are much more efficient for the prover, and these are potentially practically relevant. And some of them are related to some of the protocols that you've learned about in this class, like bullet proofs. Finally, as we already touched on in the introduction, you could also ask for stronger forms of security from zero knowledge protocols besides the definition that we've talked about so far. So you might want the protocol to be zero knowledge against quantum attacks, which we have not actually argued, because the rewinding procedure that we described turns out not to work when the verifier is quantum for somewhat subtle reasons. Similarly, the rewinding procedure we talked about does not work in a setting where you have an adversary who has opened up many concurrent executions of a zero-knowledge protocol and is trying to learn something from the joint view of many executions. And so there are lots of thoughts and techniques on how to write down protocols and prove that they're secure in these settings. So that was a brief foray into the world of interactive zero-knowledge protocols, but for the rest of the lecture, I want to talk about theoretical aspects of the Fiat-Shamir transformation and about the existence of succinct non-interactive arguments. So here's a quick reminder of the definition of a succinct non-interactive argument. So we have an NP language, we have some claim represented by a string x, and the prover, the honest prover at least, will have a witness W for the truth of the statement X. And the prover and verifier share a common reference string, either some random coins or generated via trusted setup. And then the prover uses its potentially long witness to generate a short, easy to verify proof pi that is sent to the verifier that the verifier can use to check that X is true. And as long as the prover actually has a witness W for X, then the verifier should almost always accept. But on the other hand, if the statement X is actually false, then for an arbitrary efficient strategy P star, whatever proof that the strategy generates should make the verifier reject with very high probability. Finally, as I said, we want the proof to be short, so we're thinking of this as like polylogarithmic in the length of the statement and witness, and verification should be very fast. It should be about this much time with some read access to the input. So this is what we'd like. And we've seen constructions of snargs in this class already using interactive oracle proofs along with a random oracle. There is also another family of constructions that you saw briefly using linear PCPs, but we'll be focusing on the random oracle-based constructions today. So what does it mean that a random oracle was used to convert an IOP into a snarg? Well, it's done via the Fiat-Shamir transform, which you've also learned about, but a quick recap is that it's a powerful and very general proposal for removing interaction from interactive protocols. As long as the verifier messages in the interactive protocol are truly random strings, then you can replace interaction with a verifier with the hash function h that the prover uses to generate verifier messages on its own by hashing its own messages or hashing the transcript prefixes to generate the next verifier message. What you see on the screen is just the 3-message case. So you can think of the verifier challenge as being a hash of the first message alpha, potentially along with the statement X, which is not written here. So it turns out that if you model this hash function as a random oracle, then this transformation will securely compile any constant round public coin interactive protocol. In fact, it will compile more protocols than this, but for simplicity of discussion, let's just think about constant round protocols for now. So I don't think that we've actually seen a proof of this in the class. So the first thing I'm going to do is sketch a proof that in the random oracle model, this compiler works. So now we should be a little more specific. What do we mean by the statement that H is modeled as a random oracle? So the random oracle model, roughly speaking, is an assumption about the structure of an attack on the hash function. So in principle, right, for the Fiat-Shamir protocol, the prover is given a description of the hash function, and it can use this hash function description however it likes in order to try to generate its proof. But the random oracle model is an assumption that the best that an adversarial strategy can do is treat the hash function description as a black box as a box which takes as input message alpha and spits out a message beta, and the strategy will only query this hash function as an oracle. It will not use the implementation details of the hash function. So the random oracle model is a class of attacks that tries to, in the case of Fiat-Shamir, tries to generate an accepting proof on a false statement by querying the hash function a bunch of times and not actually looking at the implementation details of the hash function. Roughly speaking, if you're only treating the hash function as a black box, it's reasonable to think of it as just like a uniformly random function. For example, the hash function could be a pseudo-random function, and then if you only query it, then it's indistinguishable from a truly random function. So the claim, very concretely, is that Fiat-Shamir works in the random oracle model, meaning that if you only query the hash function h and you don't look at its implementation, then the best prover strategy for the non-interactive protocol is not much better than the best prover strategy for the interactive protocol. And there's a security loss that grows with the number of rounds. So for the proof right now, we'll focus on the 3-message case. So what we need to do is show that any good prover, any successful prover for the non-interactive protocol can be converted into a successful prover for the interactive protocol. So we start with this prover P star, which queries the hash function a bunch of times and eventually produces a transcript alpha, beta, gamma sent to the verifier. And we want to say that we can emulate this in the interactive setting. So the key idea for proving security here is that the first message alpha that is generated by P star essentially has to come from one of the queries that P star made to the hash function h. In fact, that can be done without loss of generality. You can always assume that's whenever the prover is going to output something, it first queries the message alpha to the hash function if you really want. So, but now the punchline is that we're assuming that the prover only makes a polynomial number of queries to the hash function because it's running in polynomial time. Or more generally, it's running in some bounded amount of time, and so it has a bounded number of queries it can make to the hash function. We can take advantage of this to actually break the 3-message protocol. And the idea is as follows: if we want to trick the verifier in the 3-message protocol, well, we have this random oracle non-interactive strategy that's tricking the non-interactive verifier. And if the prover makes q queries to the hash function, then there's one of q locations essentially where it's producing an accepting transcript on a false statement for the interactive protocol. So how we'll break the interactive protocol is we'll make a guess. We'll guess which query to h is going to be the successful one, essentially. And then in the interactive protocol, we will generate the first message alpha by running the left-hand side strategy, making I-1 queries to the hash function ourselves. So I is the guess that we made for which query is going to work. So we do the first I-1 queries locally ourselves, and then we send whatever the ith query was going to be, we instead send that to the verifier. We do not query the hash function on that alpha. We just send it to the verifier. Then the verifier sends us back a random string beta, and we basically pretend that this was the output of the hash function. Then to generate our last message gamma, we continue running the left-hand side strategy until it outputs a transcript at the end. We pick whatever gamma was chosen by the Fiat-Shamir prover, and we output that. So basically, this will break the interactive protocol with probability 1 over q times the probability that the non-interactive prover is winning. Because if we happen to guess which query the alpha that the non-interactive prover outputs corresponds to, then we are, if our guess is correct, then we're correctly emulating the random oracle attack in the interactive setting. And so this says that that your security is only 1/q worse than the security that you had for the interactive protocol. For a 2R round protocol, your security loss in general will grow like 1/q to the R, roughly speaking. Although you can do better for protocols satisfying more fine-grained soundness notions like round-by-round soundness. So that was a proof that Fiat-Shamir works under reasonable hypotheses in the random oracle model. But now let's revisit this assumption that the random oracle model was making. So as we said before, the model is assuming that even though you're given the description of some hash function h, that the best an attack can do for the purposes of breaking the Fiat-Shamir protocol is treat that hash function as a black box, plug in a bunch of inputs to it, get some outputs, and use this to try to break security. So in reality, the hash function is not a random function that you call as a black box, but is instead something like SHA-256, maybe salted with some like identities, timestamps, and random strings, things like this. But it's something like SHA-256, so that's what it is in practice. But even in theory, like no matter what, you're going to instantiate this hash function with some efficiently computable public algorithm, because it needs to be something that the prover and verifier can both actually compute in a reasonable amount of time. So there is a mismatch between the model, which treats h as a random function, and the reality, which is that it's an efficient algorithm. And so, yeah, this is an obvious theoretical issue, which is that efficient public algorithms can't compute random functions. So, yeah, that's a clear issue. But nevertheless, you might still hope that for any, security property that you actually care about, that if you can prove the security property holds in the random oracle model, then reasonable hash function instantiation will also satisfy that security property. And this is the logic underlying the random oracle heuristic. So, of course, you don't just have to hope that it works. You can also try to attack any specific protocols that you implement. And so the heuristic is supported by the fact that the Fiat-Shamir paradigm has not been really broken in practice. But theorists are trying to get a more principled understanding of when and why this transformation actually works. So the first thing I'm going to show you is a negative result. We're going to see a property of random oracles, that is a security property that holds in the random oracle model, that provably cannot hold for any efficiently computable hash function family. So this is a violation of the random oracle heuristic. So here's a family of very important security properties. So there's a security property for every function f mapping strings to fixed, say, security parameter length strings. So a hash function, or hash function family, we say, is correlation intractable for this function f if given a description of the hash function h, it is computationally hard to find an input x to the hash function such that hash of x is equal to f of x. This is a very broad security property. You can plug in any function f that you like here, and you get a different security property. But it's not hard to see that for any fixed function f, you get f correlation intractability in the random oracle model. That is, a random oracle will satisfy this security property. And the reason is very simple. In the random oracle model, your attacker is just making a polynomial number of queries to the hash function. And for each query x made to the hash function, you get a random output string y. And each time you do this, the probability that y is equal to f of x is 2 to the minus lambda, 2 to the minus security parameter, which is tiny. And so even if you do this a polynomial number of times, you're extremely unlikely to find an x such that hash of x is equal to f of x. And this is true for every fixed function f. So this is a very reasonable security property that a random oracle has. And so you might expect that that if you instantiate the random oracle with SHA or with some reasonable hash function, that you'll also get this security property. But it turns out this is not the case. So there's a particular function f such that for any efficiently computable hash function family, capital H, H is not correlation intractable with respect to this function. So the random oracle heuristic just completely fails for this notion of correlation intractability. So if you haven't seen this before, now would be a good time to actually pause and think about if you could come up with a function f that proving this claim. Can you come up with a bad f where correlation intractability for f is impossible? It's an example of a very ubiquitous idea from theoretical computer science called diagonalization. So I'll give you a little bit of time to think about if you can come up with an f. So here's a function f which demonstrates the impossibility. So f is going to take as input an arbitrary string x, and what it will do is it will interpret this string x as the description of a program p. You can always, you just have some mapping between strings and programs. It doesn't matter what it is. And then f of x is equal to p of x. So you run the program that x describes on input x. So again, f takes as input the description of the program, and it runs the program on its own description. Seems like a bit of a weird function, and it makes sense because it's demonstrating this random oracle impossibility. So here's why you can't have correlation intractability for this f with an actual hash function family. So take any h, any hash function family, capital H, and we can write down a very simple attack that breaks correlation intractability with respect to this f. So given a hash function little h from this family, we want to find an input x such that hash of x is equal to f of x. So the input x that we're going to pick is the description of h itself. So we're going to take we got a hash function, and we're going to plug the description of the hash function into itself. And you can see sort of by definition that hash of x for this particular choice of x is going to be equal to f of x. Because what does f of x do? F of x plugs x into the program that x describes. X is the description of h. So therefore, f of x is equal to h of x. And so we've broken correlation intractability. Like, just given the description of h, we can efficiently find an input that is always equal to f of x, where f is some fixed function. And a random oracle does not have this property, and so this is a property that holds for random oracles, but not for any actual hash function family. This is the counterexample, and it's very simple to write down, but I think it takes quite a bit of time to actually wrap your head around. So definitely feel free to take some time to think about what's actually going on here. So let's talk about this counterexample a little bit more. Let's talk about how reasonable it is. How should this make you think about the instantiability of random oracles? So the counterexample is kind of asking for a pretty contrived security property here. In particular, this is only a counterexample to the random oracle heuristic for hash functions that need to be able to take arbitrarily long inputs. In particular, your hash function needs to be able to hash inputs that are at least as long as the description of the hash function itself. And so this counterexample does not rule out correlation and tractability for functions that have bounded input lengths. And this is very important, and it will come up towards the end of the talk, because we're actually going to build hash functions satisfying weaker forms of correlation and tractability. They actually exist. So that's one big caveat to think about here. On the other hand, there are actually other hash function security properties that holds for random oracles and provably don't hold for any hash function family that only involve fixed length inputs. It's no longer about correlation and tractability, but there are other security properties for fixed length hash functions that are counterexamples. In fact, these counterexamples are for the Fiat-Shamir heuristic. There are these two results of Barak and Goldwasser-Kalai, and they construct interactive protocols where the Fiat-Shamir heuristic applies to these protocols in the random oracle model. In particular, they're constant round protocols, and so we know that Fiat-Shamir should work. But nevertheless, they show that for any efficiently computable hash function family H, the Fiat-Shamir protocol using H is insecure. So for any particular H, there's an attack, but for a random oracle, there's no attack. So this is a very direct counterexample saying that although we have this random oracle proof of security for Fiat-Shamir, we actually have to be careful when instantiating it. There are some protocols where nevertheless it won't work. As a result, theorists are really trying to understand when the random oracle heuristic actually applies, when we can take it as evidence that the resulting protocol is actually secure when you instantiate it in the real world. So let's note a few more things about the negative result. So first of all, we break the security property in the attack we just saw by running the hash function on its own description. So you can ask, is this practically relevant? Would you ever run a hash function on its own description? If you never want to, if your protocols never care about things like this, then maybe you can say that the counterexample is irrelevant to practice. You can sometimes say this, but interestingly, snarks that are constructed via recursive composition actually do, in some sense, call the hash function on its own description. Not exactly as we wrote it down in the attack, but something that at least superficially resembles it. And that's because when you're doing recursive snark composition, what you're doing is you're giving a snark proof that the snark verifier would have accepted some other snark proof. And so you're proving things about the snark verifier. The snark verifier is running the hash function. And so therefore you want to give a snark about something to do with the hash function. So as a result, you're calling the hash function on information that depends on the description of the hash function. And so, to be clear, this is not at all to say that recursive snarks in practice are broken. We don't actually have attacks, but it does imply that there is a really hard to describe line between secure and insecure instantiations, and as theorists, we're still trying to understand what this line actually is to explain why the constructions in practice are secure, even though there are these weird counterexamples in theory. Now that we've seen some serious theoretical issues with the random oracle model, I'm going to spend the rest of the lecture telling you about some things that we can do without random oracles. So some constructions of secure proof systems that use explicit hash function families and don't resort to the random oracle model at all. So what do we do when we don't have random oracles? On what are we basing security? So what theorists like to do is make use of what are called falsifiable assumptions. So we want to construct a proof system, or perhaps some other cryptographic primitive, and prove that the primitive or protocol is secure, assuming that some concrete algorithmic task is infeasible in polynomial time, or in some not too large amount of time. So some examples of falsifiable assumptions are that computing discrete logarithms over some group is hard. Or perhaps instead we could assume that that solving random noisy linear equations is hard. This is called the learning with errors problem. This is noisy linear equations over Z mod P. So these are two very common assumptions that are made in theoretical cryptography. But you could also make an assumption like that SHA-256 is collision resistant. So it's not like so SHA-256 is not inherently an unfalsifiable object. It's the random oracle model that's not falsifiable. You can still take a concrete instantiation like SHA, and the assumption that it's collision resistant is a reasonable falsifiable assumption that we have quite a bit of confidence in. So these are examples of falsifiable assumptions, and so how things often work in crypto is we construct some cryptographic primitive or protocol based on falsifiable assumptions. But the construction is very inefficient, and so one way to improve the efficiency of the construction is often to modify the construction, making use of a random oracle, because random oracles sort of solve a lot of technical issues for you for free. They can often simplify cryptographic constructions at the cost of this modeling assumption. So for example. So I've listed some examples on the slide, but in particular for non-interactive zero-knowledge protocols, forget about succinctness for a second. Suppose you just want non-interactive zero-knowledge. We have constructions both in the random oracle model based on Fiat-Shamir, and also constructions based on falsifiable assumptions. So an advantage of having the construction based on falsifiable assumptions is that even if we end up using the random oracle-based protocol in the real world, the construction making use of falsifiability is another piece of evidence that the random oracle construction instantiated with SHA-256 is a reasonable thing to do. So our goal for the time being is to understand what kinds of protocols can be built based on falsifiable cryptographic assumptions. And so we'll start with snarks with a K. So here we're asking if succinct non-interactive arguments of knowledge can be built based on falsifiable assumptions. And here the answer is pretty quickly no. There are caveats to a lot of these impossibility results, but the intuition here should be that no, this is not something you should expect to be able to do. And so what's the issue? The issue is that an argument of knowledge wants you to be able to extract an NP witness from any successful prover. But the prover is only outputting a short proof string. So it's really unclear how to extract a long NP witness from a short proof string. And the way that the constructions we have accomplish this is by making an assumption that actually that assumes away this problem. The assumption says, oh, there is magically some way to extract a long string from a short one. So So random oracles give us this because in the random oracle model, you can think about the entire history of function calls that the adversary makes to the oracle, and this can give you a long string, even though the proof itself is short. Then constructions based on linear PCPs don't use random oracles, but they instead make a knowledge assumption over some cryptographic group, and again, this assumption like solves this problem for us. It assumes that you can magically extract large amounts of information even from an adversary that actually only explicitly tells you a small amount of information. So this is not a problem we expect to be able to solve with falsifiable assumptions, and so if you want snarks with knowledge soundness, it seems that you need to go beyond what theoretical cryptographers typically deal with. However, the situation is different for snargs with a G, or just a protocol satisfying soundness and not necessarily knowledge soundness. Here there isn't nearly so clear a reason why you couldn't build these based on falsifiable assumptions, even though the only general purpose constructions we have right now make use of non-falsifiable assumptions like a random oracle. So we don't know the answer to this question of whether falsifiable assumptions suffice at the moment. There are some barriers. There are some theoretical papers that have talked about why this might be difficult, but I would say the evidence is not nearly so clear as in the snark case, and the jury's still out probably on whether this should be possible. And for example, a lot of my personally my research is on trying to understand this question a little better. But the state of the art is that we don't know how to do this, and so we're going to settle for snargs for subclasses of computations. So we won't build snargs for any NP statement, but we'll just build them for some special NP statements that are still pretty expressive. So for the rest of the lecture, I'll sketch a construction based on the learning with errors assumption, although the details of the assumption are not that important. But this is what we're going to see for the rest of today. So let me introduce, before getting into the construction, let me introduce the two main tools and techniques that are going to come up in the construction. So the first is correlation and tractability, which we already saw earlier today. And so instead of using a random oracle-based hash function in the Fiat-Shamir paradigm, we are going to use a hash function satisfying some forms of correlation and tractability that turn out to suffice for Fiat-Shamir, at least for some specific interactive protocols, not in general. So that's the first tool. The second tool is something called a somewhere extractable commitment, which is a special kind of succinct commitment scheme. So we've seen succinct commitments in this class, like Merkle trees, but somewhere extractable commitment is a stronger form of a succinct commitment scheme, and it's used to build a special interactive protocol that we instantiate Fiat-Shamir for based on these correlation and tractable hash functions. And in the end, the interactive protocol that gets built looks a lot like the typical IOP-based interactive protocols, but only works for special languages and comes with a proof of security. So let's go back to correlation and tractability first. So as we said before, given a function f, a hash family is correlation and tractable for f if it's hard to find an input x such that hash of x equals f of x. It turns out you can think of this as a special case of a stronger form of correlation and tractability, not for functions, but for binary relations. So for every binary relation R, you could say that a hash function is correlation and tractable for R if it's hard to find an input-output pair, x comma hash of x, that satisfies the relation. And as long as the relation doesn't have too many pairs of points in it, then a random oracle will satisfy this security notion, and you could look for explicit hash functions satisfying this property. Although, again, we know that there are issues. So let's go back to the function version for a second. I spent some time earlier in the lecture telling you that this property is actually uninstantiable. There are some functions where where there's no hash function satisfying this property, no efficient one. So we're getting around this by restricting the input length to the hash function. So we're going to be considering this property for hash functions that have a fixed input length, and the description of the hash function will have to be slightly larger than this input length. So yeah, we know that this restriction is necessary, or else the object is uninstantiable. We're going to then restrict the notion even further. We're going to only consider f that are computable in some fixed, a priori bounded polynomial time, capital T. So our goal is going to be to build a hash function that's correlation intractable for all functions f computable in time t, and the hash function itself will be computable in time slightly larger than t. So this is what we know how to build right now. It's not clear if this restriction is necessary, but yeah, that's currently what we know how to handle. So next, I'll actually show you a construction of such a hash function family based on a falsifiable assumption. And our main tool for doing so is something called fully homomorphic encryption. So this is a kind of encryption scheme where you can encrypt some data x, and on the ciphertext encryption of x, it is possible to evaluate an efficiently computable function f of your choice on it, and obtain an encryption of f of x. And this you can do without the secret key, without knowing what x is. Just given an encryption of x and the function, you can evaluate it under the hood. The guarantee of the homomorphic encryption scheme is that if you were to decrypt the evaluated ciphertext, you would get f of x. So this is a very powerful tool, and is not necessarily practical, although people are spending a lot of time trying to make this practical. It's not actually necessary for to construct the hash function, but I'm going to use this high-powered tool because it gives the simplest or the easiest to explain construction. But there are other constructions that do not use fully homomorphic encryption. But nevertheless, let's see a construction using it. So given a fully homomorphic encryption scheme, we're going to write down a hash function family and then argue that it's correlation intractable. So here's the family. So the description of a hash function h is going to be two things. First of all, a public key for the homomorphic encryption scheme, and then an encryption of the description of some function g. You should think of g as some function that just takes every input and output 0 immediately, or something like that. It's not too important what this function is. In fact, in reality, you can think of the description of our h as actually being a uniformly random string. But in our heads, we will think of it as a public key and an encryption of a function g. And as long as the encryption scheme has the property that public keys and ciphertexts are pseudo-random, then a random string is indistinguishable from such a hash function description. So we can equivalently think of it as a random string or having this structure. Okay, so this is how we're going to think of a description of the hash function. So now we should say what the hash function actually is. That is, given an input x, how do you hash it? So what you do is you run the FHE evaluation algorithm on the encryption of g, and the function that you use is described by x. So what you want to do is evaluate the function, which takes g, which is encrypted, and computes g of x. So this is sort of like inverting the usual way you think about inputs and functions, but this is something that you can do. So yeah, so the hash key is an encryption of G, and when you hash X, you will get an encryption of G of X. But hashing X is a public efficiently computable operation. Yeah, this is a hash function that you can write down. And so why would we expect this hash function to satisfy security properties of any kind? Well, the reason is that the function G is hidden. It's implicitly in the description of H, but nobody actually knows what it is. And so you can argue different security properties by imagining that G were various different functions. Because an encryption of G is indistinguishable from an encryption of some other function G prime, you can imagine that G was whatever function is most convenient to you for proving some security property. So let's see. That's a little abstract, so let's just see a proof that this hash function is correlation intractable. So we'll do a proof by contradiction. Suppose that for some a priori fixed efficiently computable function f, an adversary could find an input x such that hash of x is equal to f of x. Well, then, so here's the key idea in arguing security. We're going to pick a very special function, g star of x. What it's going to do is it's going to compute f of x and then decrypt the resulting string. So you think of f of x as a ciphertext. You decrypt it, so now you have some plain text. You can think of the plain text as being a single bit if you want. And then you, after decrypting, you add 1. So, this is a function that you can define. And we know, like I was saying before, that an encryption of whatever G we started with is computationally indistinguishable from an encryption of G star, provided that the encryption scheme is secure. So there is a minor caveat here, which is that the G star that I defined actually runs the decryption algorithm of the encryption scheme, and so it depends on the secret key of the encryption scheme. But we can still argue this indistinguishability if we know that the encryption scheme is secure in the presence of an encryption of the secret key. And so this is called circular security, and it's something that comes up pretty frequently in homomorphic encryption, and it's something that we're reasonably confident in. But this assumption is not really necessary. You can get away with less with a more complicated construction. But we're going to assume this circular security for now, just for the easiest construction and proof. So okay. So we started with a hash function, which was an encryption, which was described by an encryption of G. But because an encryption of G is indistinguishable from an encryption of G prime, then we know that our attacker would still break security, even if it were given an encryption of G prime instead. But now I claim we have a contradiction, that the attacker actually can't break security when the hash function is an encryption of G star instead. So here's why. So we know that if you hash X and your hash key has an encryption of G star in it, then hash of X is going to be an encryption of G star of X. So then we can see that, so if, on the other hand, hash of X was also equal to f of X, that's what we're assuming. We're assuming the adversary managed to find such an X. Then we would get that, so if hash of X is equal to f of X, then if you decrypt f of X, then this is supposed to be the same as the decryption of hash of X. But we also know that hash of X is an encryption of G star of X. So decryption of hash of X is equal to G star of X. And we've defined G star to always avoid the function decryption of f of X. It's literally 1 plus decryption of f of X. So these two plain texts cannot be equal. The scheme has been constructed so they can never be equal. And therefore, it is actually impossible for the adversary to break security when the hash key is sampled in this strange F-dependent way. But by indistinguishability, that also means that the adversary can't do it when the hash key is a random string. So this is a proof, assuming that your encryption scheme is secure enough that the resulting hash function is correlation intractable. So that's one construction of a correlation intractable hash family for efficiently computable functions. So there's been a lot of work over the last 5 years or so in constructing various correlation intractable hash families, including for relations that are not just functions. So I'll list a few on this slide. So when you restrict to functions, we have constructions based on the learning with errors assumption. So we know, so LWE can be used to build fully homomorphic encryption, but follow-up works were actually able to avoid making this circular security assumption that I made in the proof on the previous slide. So you can really build it based on the standard hardness of learning with errors. There's also a construction from the decisional Diffie-Hellman assumption, so which is more related to some group-based cryptography that you may have seen in this class. So LWE lattices and DDH groups are the two main families of building blocks and assumptions that are used by theoretical cryptographers, and both of them we now know how to use to build correlation intractability for at least some kinds of efficiently computable functions. The DDH-based construction is actually restricted to certain subclass of functions, but it's pretty expressive. Then you can ask, well, okay, what about relations that are not functions? Although it's still not clear why we're asking any of these questions, but you could ask, what about things that aren't functions? We don't know in general whether or not we can build correlation intractability for bounded input length relations, but we do have a construction for relations satisfying a nice combinatorial structure. Basically, if you think of the hash value as a concatenation of many blocks, then you can guarantee correlation intractability for properties that sort of respect the blockwise structure, and this turns out to be relevant when instantiating Fiat-Shamir. Don't worry too much about this, but so we can handle some kinds of relations that have many outputs, but it's still somewhat open how to handle them more generally. That's everything I wanted to say on constructions of correlation intractable hash functions from falsifiable assumptions. So for the rest of the lecture, we'll talk about how to use the hash functions that we constructed to provably instantiate the Fiat-Shamir heuristic without relying on random oracles. So the basic paradigm for how to use correlation intractability is that we'd like to avoid some notion of bad challenges. So on the slide, I have up the transformation for 3-message interactive protocols. And so here's, and in this setting, we'll consider the following analysis. So given an initial statement or initial claim X, which is false, and a first message alpha that is adversarially chosen by the prover, we say that a verifier challenge beta is bad if there exists a prover message gamma making the verifier accept. And it'll become clear in a moment why this is the definition that we're writing down, but let's just go with it for now. So in the interactive setting, we'd like to say that soundness of the interactive protocol implies that most challenges are not bad. Specifically, we want to say that for any false x and for any message alpha, that most beta the verifier could pick are not bad. So this is true for statistically sound proof systems, but not true for computationally sound proof systems. In fact, if the interactive protocol is only computationally sound, it might be that every message beta is bad. It might be that every challenge is bad. It might be that for every challenge, there exists a message gamma that would make the verifier accept. But the protocol could still be sound because these gamma might be hard to find. But if you start with a 3-message protocol that is sound against unbounded provers, then the soundness actually directly says that for all false x and for all alpha, most beta are not bad, because whenever beta is bad, the inefficient prover could trick the verifier. So, long story short, if we start with a statistically sound protocol, which is a major caveat, but nevertheless, if we start this way, then we get this interesting fact that most beta for every fixed transcript prefix, x and alpha, most beta are not bad. So this is exactly a situation where correlation intractability seems useful. In particular, we can talk about a relation whose inputs are first messages alpha and whose outputs are second messages beta. And we can say that alpha beta is in this relation if beta is a bad challenge for alpha. So this depends on the initial claim x. So what you actually get is a relation r sub x for every false statement x. Or you could alternatively have a single relation whose inputs are x comma alpha and outputs are beta. And then this is in the relation if x is false and beta is bad. So in any case, there are some relations that we can write down, and it's pretty easy to see that if the Fiat-Shamir hash function h is correlation intractable for these relations when we're dealing with false statements anyway, then the Fiat-Shamir protocol is actually sound. And the reason is that if you break the soundness of Fiat-Shamir, then whatever first and second message, alpha and beta, you end up sending, no matter what that pair is, it must be that beta is bad for x comma alpha, because in fact you even found the third message gamma making the verifier accept, so you've solved an even harder problem. As a result, breaking Fiat-Shamir is an attack on this particular kind of correlation intractability. So, in fact, we can, so this is a way to relate correlation intractability to Fiat-Shamir for 3-message protocols, but for you can extend this actually to protocols with arbitrarily many messages, provided that they satisfy a statistical form of round-by-round soundness. That is, for every round, for every verifier message, you can talk about a notion of that message being bad, and as long as the hash function avoids these bad messages, then you'll get a secure Fiat-Shamir instantiation. So this is the high-level approach for how correlation intractability implies Fiat-Shamir instantiations, but there are some big technical challenges in order to actually show that this works. So first of all, sometimes you don't start with an interactive proof that is actually statistically sound. And then so far what I've said says nothing about how you might instantiate Fiat-Shamir for such proof systems. We'll discuss how to handle this a little bit in the next slide, or in a particular example. The second technical challenge, which I'm not going to cover in this lecture, but you can see some of the papers for details. The second challenge is that we only can build correlation intractability for specific kinds of relations. In particular, all of the relations that we handle have the property that they can be decided in polynomial time. But the relation that we just talked about, that alpha and betas in the relation if there exists a gamma making the verifier accept is not actually decidable in polynomial time, and so it's not clear. How anything that we've said so far helps there either. I won't cover really how you handle this second challenge, but from the example that we are about to get into, maybe you could see how that might go. So now let's focus on a particular example. Let's focus on the problem of obtaining snarks and via interactive oracle proofs, which you've seen a few times in this class already. So here's a very simple template snark using a very special kind of interactive oracle proof, which is called a probabilistically checkable proof. So this construction is due to Killian and Macaulay from the 90s, and it's essentially a theoretical simplification of some constructions that you've already seen in class. The cost is that the downside is that this construction is way less efficient, but we don't need to worry about that for now. So way less prover efficient. So here's the protocol. So the prover starts with a statement X along with a witness W. And what the prover is going to do is, first of all, compute some long proof string pi from X and W. It's some sort of encoding. And then you can think of pi as being the analog of the oracles that you saw in the IOP-based constructions. And then the prover commits to this very long string pi. It sends a succinct commitment to the verifier. The verifier then samples a random string which indicates a set of locations or a set of indices. It indicates a substring that the verifier wants the prover to open, and the substring should be very short. Then finally, the prover gives local openings to every location that the verifier asked for. So this is like a minimally interactive version of the IOP-based snarks that you've seen before. And instead of using a polynomial commitment, we're just using a vector commitment. Good. So this is a very basic construction, and you can prove that as long as the mapping from as long as the information theoretic object pi, as long as that underlying proof system is sound, then the resulting interactive protocol here is also sound. So then you immediately get a candidate snark as well by applying fiat Shamir to this protocol. However, as I said, this is a more inefficient version of modern snarks that you've learned about in the course already. But it's easier to talk about this version because there are fewer moving parts. So in principle, we have a candidate snark, but since this interactive protocol is not statistically sound, it's really not clear how anything I've said about correlation and tractability can help us argue the soundness of the fiat Shamir version of this protocol. So the reason this protocol is not statistically sound is because whenever you can find collisions in the vector commitment, then this protocol will be broken. Or sorry, if at least if you can find good enough collisions in the vector commitment, then this protocol will be broken. Okay, so what do we do? What we're going to do is we're going to restrict the kinds of computations that we imagine that we're proving. So we're going to, instead of considering the problem of proving an arbitrary NP statement succinctly, we're going to imagine that we're proving a large number of small NP statements. So instead of one big computation, imagine we want to prove that many small claims are true. So this is called a snark for batch NP, and the syntax is that the prover is given k statements, x1 through xk, and k witnesses, w1 through wk, sends a proof pi to the verifier. The verifier has these k statements, And what we want is that the verifier will accept the honestly generated proof if every one of the witnesses is a valid witness, if Wi is a witness for Xi. And moreover, if any of the K statements is false, then no matter what the prover does, for any efficient prover strategy, the verifier is likely to reject. Then we still ask that this proof is succinct, but the succinctness notion that we ask for is different. We want the proof length to have polylogarithmic dependence in the number of statements K, but we allow it to be at least as large as a single witness W. So that's why I said the situation to have in mind is that you have many small NP statements. The proof is still succinct because the naive proof would require sending K witnesses, which would be very long, and you'd have to verify K different claims. But the proof length and verification time here has a logarithmic dependence on K. So this is not as strong as a full-fledged snarg for arbitrary NP statements, but it's actually a surprisingly powerful object. It's been shown within the last couple of years that, for example, if you have such a proof system, then you can use it to build a snarg for any deterministic computation. So that's another restricted class of computations where there's no witness, but just like checking the claim X yourself would take a very, very long time. And a snarg for deterministic computation has the prover send you a short proof that you can verify very quickly. So in any case, the point here is that snargs for batch NP are pretty powerful, and we're going to show how to build these using correlation and tractability. This is a construction due to Chowdhury, Jain, and Jin from 2021. So here's a protocol, an interactive protocol that looks a lot like the previous succinct argument that I showed you, the Killian-McCauley construction. All that's happened is that instead of writing down a single PCP, a single proof string for a single witness, you now write down K of them, one for each one, and then you send a succinct commitment to all K of these proof strings. The verifier then does the same thing as before. It samples a location set, but now the prover is going to give you local openings to answers for all K of the proofs. So this is a protocol that you can write down. So if you're concerned that this proof doesn't seem succinct, don't worry about it. We're going to make it succinct later, make it more succinct later. But it's at least somewhat succinct. You do not have to send. This is still less than K witnesses worth of information that you've sent here. So why did we switch to the batch verification setting, and why did we write down this protocol? Well, there's a clever idea here that reduces us to a protocol which is kind of statistically sound. So the idea is that you can use a commitment scheme which is statistically binding to one out of the K proofs that the honest prover was supposed to generate. So, of course, if the commitment is succinct, you can't be binding to the entire concatenation, pi 1 through pi k. Then your commitment would have to be at least that long, and then you have no succinctness. But you could be statistically binding to a single one of them. So it could be that a commitment information theoretically determines, say, the first proof, pi 1. So if that's the case, then if the first statement, x1, is false, then this protocol, for this like collection of for this statement anyway, would be statistically sound. Because you're information theoretically bound to this particular proof string, then it turns out there are only a small fraction. I mean, by the soundness of the information theoretic proof system, you can only successfully answer a small fraction of the queries represented by the verifier challenge R. So if you use this special kind of a commitment scheme, then you can be statistically sound when you are told that a fixed statement like x1 or xi is false. So let me say a little bit more about this notion of a commitment scheme. It's a property called somewhere statistical binding. So somewhere statistically binding commitments are strengthening of the usual notion of succinct commitment, which I'm going to think of as a Merkle tree, like you've seen in the course so far. So we say that a Merkle tree type construction is somewhere statistically binding if for every index, index of your initial vector, there is a way to choose the hash key such that the roots of the Merkle tree information theoretically determines that single location of your vector, that single coordinate. So formally, what you ask for is that for every index I, that there is a way to sample a hash key depending on I, so that when you sample the hash key in mode I, you have statistical binding to the ith position of your vector, and moreover, the n different ways of sampling these hash keys, one for each index, all have to be computationally indistinguishable. So it's statistically binding somewhere, but you don't know where. If you're just given the hash key, you don't know which coordinate is bound. But one of them is bound, but it could be any of them. And so it turns out that you can build such commitment schemes. I'm not going to get into the construction, but it's possible to construct these. And yeah, so you can think of when the hash function is sampled in mode I, you can think of the Merkle root as secretly encoding the particular coordinates, the ith coordinates of your initial vector. So so this is the kind of commitment scheme that we want to use in this construction. So now the idea is that you can argue soundness of this protocol, and in fact, in the following way. Suppose that one of the statements, one of x1 through xk, is false. Then you can switch to a world in which the hash key was sampled to be statistically binding on the ith PCP, where I is the index of the statement that's false. Right? If you break soundness, then you break soundness on any of these, no matter which mode of hash function you choose. And so you will imagine that the hash key is sampled in that mode. Then you have a protocol which is actually statistically sound, and this actually enables you to rely on correlation intractability to prove the soundness of the Fiat-Shamir protocol. I won't get into the details of the argument, but the idea is that, for any particular index I, if the ith statement is false, you can rely on correlation intractability for some relations that depend on the ith statement and the proof string that's statistically committed to by the Merkle root. And you can combine this with the correlation intractable hash functions that we've talked about to argue soundness of the Fiat-Shamir protocol. Now, one last detail, which I should mention, is that right now the protocol that we've written down is not fully succinct. Its proof length is like security parameter times the sum of the length of one witness and k. But what we wanted was essentially no k dependence, or maybe a polylogarithmic k dependence. But you can actually do this by recursion. So what you can think of this protocol as having done is it's reduced verifying k witnesses, w1 through wk, to verifying k openings of a small subset of locations to the PCP. So you've reduced you have a reduction from a larger amount of work to a smaller amount of work, and this enables you to recurse. You can then use this proof system to, instead of actually sending the openings in this third round, you can instead commit to some information related to it and have a longer protocol that eventually reduces your work down to nothing. Then you can argue soundness of the Fiat-Shamir protocol via a round-by-round argument. This concludes our discussion of constructing snarks for batch NP computations without relying on random oracles. Let me give a quick summary of everything that we've talked about in the second half of the lecture. So the basic idea is that we could hope to instantiate Fiat-Shamir without random oracles by relying on an appropriate notion of correlation intractable hash functions, where we have to balance that the strong notions of correlation intractability are hard or impossible to build, but the notions that we use still need to be strong enough to capture the security of the Fiat-Shamir transform for particular protocols of interest. So there have been a bunch of works over the last few years that have given different constructions of correlation intractable hash families and then applied them to build non-interactive protocols that we care about. So, for example, we know how through this approach to build non-interactive zero-knowledge protocols based on quote-unquote standard cryptographic assumptions. Here we've given up on succinctness for the moment, and we're just going for zero knowledge. We also know how to make the sumcheck protocol non-interactive using a standard model hash function using this approach. And this also enables you to do certain kinds of snarks by using the GKR protocol, which I think maybe you haven't learned about in the class, but it's an extension of the sumcheck protocol that allows you to delegate certain kinds of deterministic computations. And then finally, there's the construction that we just sketched, which is how to do snarks for batch NP computations, again using a standard model Fiat-Shamir. And as I mentioned, this can be used in turn to build snarks for arbitrary deterministic computations. So let me mention also a couple of the biggest open problems, in my opinion, in the area. So first of all, we really still don't know how to characterize which interactive protocols can be soundly compiled via the Fiat-Shamir transform without relying on random oracles. We know that what the random oracle model predicts does not match reality. There are some protocols where there's no hope. On the other hand, we have some positive examples where it is possible, but there's this huge middle ground of protocols that we don't know how to analyze nor rule out. And this includes, for example, the IOP-based snarks for NP that you've learned about in the class so far. We don't know what to say about those. And that's a big open question. And relatedly, we still don't know whether snarks for NP can be built based on falsifiable assumptions. I mentioned there are some barriers here, but on the other hand, we have these provable snarks for subclasses of NP computations, and I'm actually somewhat optimistic that we can expand this class to be larger and larger, and eventually maybe even answer this question positively. I'm hopeful that in the next, say, 5 to 10 years of research, we're going to learn a lot about these questions. So this concludes the lecture. I hope that, among other things, you've learned some cool theory behind the protocols you've been learning about, and seen a somewhat different way of looking at and thinking about these protocols that will give you another tool in your arsenal wherever you might go after this. So thanks for listening, and see you in the next lecture.